We're gonna start with basically an overview over the cosmic distance ladder. I'm gonna explain a little bit what the cosmic distance ladder is, why we need it, and we're gonna give some examples. Why do we need distances? We wanna have like a three-dimensional picture of our environment, right? Which is already pretty well established, I guess, for our local neighborhood in generally. We need to draw the right conclusions towards the properties of the objects we're looking at. As long as we don't know how far away it is, we cannot really say much about the actual properties. We wanna draw conclusions towards the physical properties like size and luminosity. Size, luminosity. For example, I mean, there are many other things like metallicity. Like you have two stars on the sky. They look exactly the same. They might appear the same, but it doesn't mean that they're actually the same. One of them could be at a greater distance, and then they have completely different intrinsic properties to actually appear the same to us. What scale are we talking about? Same galaxy. We're talking the whole scale. So what we're gonna do today, we're gonna scale up, right? We're gonna start in the solar system a little bit and then we scale up. Now, if we talk about stars, if I talk about stars, I talk about our galaxies. We can resolve some stars in other galaxies, like very, very bright stars, like a supernova happens or Cepheids. But usually resolving single stars is like limited to our own galaxy, yeah. If we know the distance, we can draw the right conclusions towards the actual physical properties. Even if the stars appear the same, doesn't mean they have to be the same. Lots of different methods available. And that depends on the objects. Not all of them are suitable for all the objects, right? There are different objects we can use for that. Like star clusters, planetary nebula, single stars, whole galaxies even. And depending on the objects, then we can use different methods, yeah. For example, close objects, as objects that are close to us, are suitable for simply geometrical methods. Geometrically methods, but only if they're very, very close to us, when we can resolve them very, very good, in a very good way. On the extra galactic scale, this is no longer possible because we cannot resolve the stars anymore, yeah? Extra galactic scale. Not possible because stars can no longer be individually resolved. There you go. Okay, so this is for close objects, and the farther out we go, the more important becomes the cosmic expansion, right? The further away, the more important is the cosmic expansion. And because all of this is very difficult to achieve, so distance determination is difficult to achieve, and that's why it's conventionally based on something called the cosmic distance ladder, okay? Yeah. Conventionally based on the so-called cosmic distance ladder. If we have, I mean, they call it ladder, it's very visually, right? So we have a ladder here, and with different steps. And to reach the last step, right? You have, before you go there, you have to do all the other steps. You have to start on the bottom. I mean, usually that's how a ladder works, right? I don't know. I don't know about you guys, but I think that's how a ladder usually works. We're gonna start out with the solar system. There you go. Historically, everyone knows Kepler, right? Who doesn't know Kepler? Astronomer Johannes Kepler in the 17th century he built on Copernicus' work, Nicolaus Copernicus. Earth goes around the sun. I mean, you know, there was a time when they thought that everyone revolves around the Earth and the Earth is the center of everything. But of course, that is not how it is anymore. Yeah, we wouldn't know that for a long time, yeah. So what Kepler did, he found out not only do the planets go around the sun, he also found out that they go that they are not on circles, that they are actually on ellipses, right? So realized orbits are ellipse, which is the first Kepler law, by the way. So first Kepler law. I mean, eventually Newton would build on that, right? Newton would build on this for his theory of gravity. And then Einstein would build on this for his general relativity. That's why we have this quote, we are standing on the shoulders of giants, right? So something came before. We're not able to just learn it all. At one point we have to trust what people came up with before us, right? Instead of just inventing it all over again. So what we use though for distance estimation in the solar system is the third law, right? Kepler's third law. Kepler third law. That is used for distance estimation in the solar system. And what it says basically, I mean, let me write this formula here. Just to give you the formula. So what it basically said is that the square of the orbital period is proportional to the cube of the semi-major axis, right? So if we have the sun here, and we have the planet here on an ellipse, so let's say this is Earth, then this is like the semi-major axis A. There's also the minor axis, the short one. So the square of the orbital period which is P, yeah? So this P here is the orbital period of a planet, is proportional to the cube of the semi-major axis of its orbit. Of its orbit. And the semi-major axis, which is A. Okay, this is A. So that is basically that is the law. That is the Kepler's third law. But this is the gravitational constant, and the big M is the mass of the sun, and the small m is the mass of the planet, right? And what we do with this is we can compare it basically to our Earth. Let's write it down here again. Now you get like a good idea how all this works. We say, well, the mass of the sun is so much bigger than the mass of the planet. Let's just ignore it, okay? Let's just say, okay, we don't need it. So we say it's way bigger. The mass of the sun is way bigger than the mass of the planet. So the whole formula is then reduced to G big M. Bam. We ignored it. We said, we don't want this. We don't want this. We kick it out. We kick it out. So, let's say we have another. This is Earth, okay? Earth. Now let's say we have another planet here. I don't know. Mars? Let's call it Mars. Huh? Okay. So we say, well, this we're gonna make this a smaller factor. We're gonna make a substitution for this, so we don't have to write it down every time. So we say this symbol now represents this part of the equation. Then the equation becomes this. And we say, okay, this is the period of Earth, and this is the semi-major axis of Earth, okay? And now we introduce another planet, Mars. So we have the period of Mars and the semi-major axis of Mars, right? And we're just gonna rearrange this formula. We rearrange it to replace this. We put that in the Earth formula, and what we basically end up with is something we can compare, right? We have then the period of Earth squared, the period of Mars squared equals the semi-major axis of Earth's cube and semi-major axis of Mars cube. What we can then do is, even without knowing the semi-major axis, we don't even need to know the value of the semi-major axis. We can then calculate the distance in terms of how far or close it is to Earth, right? So we know we can say the period of Earth. What is it? 1 year. 1 year. The distance of Earth? 1 AU. We don't need to know how far away 1 AU, right, is to calculate it in terms of Earth. What we then do, we look at the sky, we see, okay, we can look the period of Mars, right? We can look it up. We can look at the sky. We wait until Mars goes around, the sun, and we know, okay, that's how long the period is of Mars. And then we can just put it in the formula, which we can rearrange to the semi-major axis of Mars, and then we come up with that Mars has a semi-major axis in terms of Earth a distance, right, without knowing the exact value of 1.5 AU. Do you understand this? Any questions so far? So what we do is we measure orbital period of another planet. In terms of AU, yeah, in terms of AU, yeah. Mu equals here. Yeah, sorry, Maximus. Spot the physics students. You forgot a minus. You forgot an equals. 1 AU is the Earth's distance to the Sun, okay? That's what we assumed. I should have probably said that. Just use our Sun. So what they did back then, they used the Venus transit actually, yeah. So the Venus transit was very good to determine this geometrically. One way would be the Venus transit. It's not something that was easy to achieve back then because like they didn't have the good telescopes, right? So what happens if you like, let's say we're on Earth, like this is Earth. This is Earth. So there's Maximus, this is Maximus. Okay. This is Vash. Okay. Let me see if I can draw it correctly. There's the sun. And there's Venus. Bam. Going right in front of the sun. I should have made the sun bigger. Wait. We make Venus there. I think we put Venus there. I need to draw it somehow. I hope I draw it correctly, but let's see. So Maximus is looking at Venus to the sun. There, his line of sight makes it that, damn, Venus is there, in front of the sun. Now Vash is here, also looking at Venus. The line of sight is different, and oh my god, you're lying, Maximus. It's not actually there. It's there. So yeah. They see it on a slightly different position. That is exaggerated. That is not how it actually is, okay? It's like way, 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 way smaller, if you will find out. And they were able to use this to determine the distance to Venus. Now I think I wrote down the numbers exactly they came up with back then. Yeah, so apparently, 1639 there was a Venus transit, and they determined 96 million kilometers. Then in the next transit, 1761. The Venus transit come like in pairs of 8 years, by the way, so which is interesting. And apparently it has something to do with the fact that 13 Venus years go in 8 Earth years or something like this. And they said, okay, it's 151.7 million kilometers. using geometry by measuring the event at 2 different points of Earth. At 2 different points. What is the actual distance to 1 AU? I mean, nowadays, what do we have nowadays? Nowadays we have lasers and we have radar, okay? So nowadays, laser, radar, and 1 AU equals precisely, I have written that down too somewhere, hopefully. 870.700 kilometers. Mean distance. This is the mean distance. It's ellipse, so it's not a real radius, of course, since it's not circular. So at one point Earth is farther away from the sun, and at another point it's closer to the sun, and this is basically the mean distance. No, this is the distance of 1 AU, and 1 AU is the distance from Earth to the Sun. We're just using Venus to find out what it actually is. So that is like a little bit of an historical overview. Now the cosmic distance ladder. The first step is using this geometrical effect. But this is just the first step. What we need for the cosmic distance ladder is objects where we can determine the distance with confidence, okay? Objects where we can determine the distance with confidence. Because it's a ladder, right? The error's gonna accumulate. If you go higher on the ladder, you have more errors. So that's why we need to be really sure with the previous step to do this, okay? Distance is usually given parsec. I know everyone uses light years mostly, but like when we talk about it in media and all of that, but actually in astrophysics, distance is given in parsecs. It's short PC, used for long distances in astrophysics. Them. 1 parsec equals 3.26 light years, which equals 3 to the power of 13 kilometers. The most important property here is how bright a star appears to us, and when we want to find out the distance, that is actually how bright the star or the galaxy is to us is the most important property in general. So how bright an object appears to us is most important property. Because we're going to talk about magnitudes a bit, okay? We're going to talk about magnitudes. Magnitudes. What are magnitudes? Stars have a range of brightness, right? Stars, I like galaxies, whatever. But I mean, the galaxy is bright because of the stars inside. So let's say stars, yeah? Range of brightness, brightness because of a different radius, for example, different radius. We use R for this, or like different temperature, right? T. There you go. So a higher temperature will, and a larger radius will usually increase in more luminosity, right? So it's emitted, yeah. So higher T, R, more luminosity. Higher luminosity. Higher luminosity. Luminosity. And the brightness of a star is conventionally given in magnitudes, okay? Brightness of a star is conventionally given in terms of magnitudes. Unitless, by the way. Unitless. They don't have a unit, which is nice. Everything that doesn't have a unit is nice to calculate with. And it's defined in such a way that the brighter objects have a lower value. Yeah, make sense out of this, guys. Defined that brighter objects have lower values. Even going into negatives, yeah? We're even going into negatives with that. And there are two different magnitudes. There is the apparent magnitude. Is labeled with a small m. So the apparent magnitude says how bright an object appears to us from Earth. For example, the sun has an apparent magnitude from about minus 27. Venus has an apparent magnitude of about minus 5, while Pluto has an apparent magnitude of about 40. It's defined in a way that the Vega, the star, has an apparent magnitude of 0. So that's how the scale is defined. And suddenly you don't have to jingle larger numbers anymore of luminosity if you want to like tell someone how bright something is. You can just use the magnitudes. It's nice, actually. It's really nice. Absolute magnitude. Hi, Lelling. Paying my dues. Thank you, Lelling. Thank you. So the absolute magnitude. You guessed it. You guessed it. It's right. Capital M, right? Capital M for absolute magnitude. Is the absolute magnitude gives how bright the star would be if the star would be not at the distance it actually is, but it would be 10 parsecs only away from us. How bright the star would be. How bright a star would appear to us if it would be 10 parsecs away from us. That is what the apparent magnitude says. Okay? That cannot be measured. We can't measure that. How are we gonna measure it? We can't go to the star. So, cannot be measured. We can't go there. We can't go there 10 parsecs away and measure it. The Greeks already did catalog the magnitude. So the concept of magnitudes, it's not a new one. It's a very old concept, and we have done it since the Greeks, basically. So we cannot measure the absolute magnitude, and we need to find out, basically, over other ways how we do this. And for this we use, for example, standard candles. Okay, so it's another term I want to tell you right now so you know about it. What are standard candles? Standard candles as a class of objects which with a well-known intrinsic property, or like a well-known extrinsic brightness due to a certain physical property. Yeah, okay. It's a class of objects with a well-known intrinsic brightness due to a certain physical property. So we're gonna come back to that. We're gonna come back to that term standard candle. Just remember it right now. We're gonna go to the first step on the ladder now. We have 3 basic steps. Okay, I'll write it down here. Okay, 3 basic steps on the ladder, on the cosmic distance ladder. So the first step is trigonometric parallaxes from nearby stars. So trigonometric parallaxes. We talked about this. I showed you the Venus effect, right? So we're gonna explain it here a little bit in a different way. So this uses the visual perception where a object changes its apparent position, not the actual position, the apparent position. Compared to a background that is further away, right? Compared to a background further away. That is like a visual trick that is done. That you don't need to look to space to see that, right? You can see that on Earth in real life all the time. So this visual perception effect is larger for objects that are closer to us, or a stronger, larger effect for closer objects. We use the fact we were talking about earlier with Venus. We are looking at the same object. Oopsie. Of the same object from 2 different positions. Which causes an angular shift of the objects. This angular shift is called parallax, okay? which represents an angle. I'm just gonna draw something here because that is probably better to do. So we have the star here. Orbit. Earth is orbiting the, or like, yeah, this is the sun. We have here Earth. Let's say this is Earth in spring. This is Earth in autumn. Earth is orbiting around the sun. Are we also gonna talk about protomolecule? No, probably not. Now there's a star. We look at the star. Autumn. Oh. Okay, good. Thank you, thank you. Autumn. A happy little star. A happy little star. Should we make it yellow? I don't know. I feel like bad. Oh, I feel bad. I make everything just in gray. But I'm so I'm so lazy today. So this star has a certain distance to us, right? There. That's the distance. D. Let's call that D. Now we want to know how far, how is D? Like, what is D? D? Huh? What? So here on Earth, there, let's say there's Chris. Chris is observing the star from here. All right, and here we have Baleur. Baleur's observing the star in autumn. Actually, yeah, this is a different time. Wait, we don't even need different people. It can be the same person. Okay, this is Chris again, and this time Chris is observing the same star in autumn. So this is not actually the star, right? It just appears here. It's an it's the apparent position on the sky in autumn. And here, that is the apparent position. On the sky in spring. And bam! There's an angle, trigonometry, case closed, done. Right? You all had trigonometry in school, I assume. It's important to note that the actual position of the star has not changed. God damn it. Has not changed. It just appears like it has. The angle, this angle is a very, very small angle, okay? We're talking about very, very small. And it's measured in arc seconds, which is, you note like this two little quotation marks. It's like, it means arc seconds. It represents a triangular angle, right? For 1 arc second, which exactly is the distance of 1 parsec, and then you just can calculate the with this formula. Okay, now the problem is accuracy decreases the smaller this angular is, right? Accuracy decreases the smaller the angle is, which is in turn smaller the further away the object is. Okay. But the very important thing here, and that needs to be noted, is for the first step, no assumption of any intrinsic property needs to be made. Needed, okay, needed, yeah. We don't need to make any assumption about any properties of the object. We can just use pure geometrical relations, right? It's a pure geometrical relation. We don't need to know anything about the star. We don't need to know the brightness or anything. It just needs to be bright enough so we can see it clearly. We can resolve it singularly, and then we can use it. It's the most direct approach. Okay, good. We're gonna see later the difference. The problem with this approach is it's limited to objects close to us. Yeah. Problem. Wow. Limited to close objects. Close objects. The angle is very, very small, and the farther away is, the smaller becomes the angle. Eventually, you cannot resolve the stars any longer in a way that this makes sense. I don't know if you heard about the Space Observatory Gaia, yeah? Space Observatory Gaia has measured I don't know how many, like billions, I don't know how many stars. Measured parallaxes since 8 years, since 7 or 8 years, I don't know, since let's say 7 years, of countless of stars, yeah? And this is in our solar proximity, yeah? Okay. In our solar proximity. And the distance it can achieve up to up to 1 kiloparsec. Yeah, do I have that right? Yeah, 1 kiloparsec. And just a reminder, our sun is 8 kiloparsec from a galactic center, and our Milky Way has a diameter of, I think I have it here, 30 kiloparsec. 30 kiloparsec. So we built a space observatory, and we only can go 1 kiloparsec. We cannot. The first step of the distance ladder doesn't even cover our whole galaxy. Doesn't even do that. So, first step does not even cover our whole galaxy. Even though we have built a space observatory for that. But what we can do, by the way, Gaia is at the same spot as the James Webb Space Telescope is. They're both in Lagrange point 2. Yeah, Lagrange point 2, by the way. So, yeah. They're both together, guys. They're not alone. They're not alone. They can have a little space party at Lagrange point 2. Isn't that nice? So, but... god damn it. It can be used as stepping stone for the next step. Second step. Damn. Now we go back to standard candles, okay? For the second step we use standard candles, a standard candle, glass stars called the saphites. We now at the second step of a distance ladder where we use saphites, which is a class of standard candles, to determine the next step of the distance. What are saphites? Saphites are variable stars that change their luminosity periodically. Variable stars that periodically change, okay, let's say increase and decrease their brightness. The period P, which we note as P, can range between days or months. Days, months. Depending on the intrinsic brightness, luminosity of the star, okay? Intrinsic brightness. Damn it. Of the star. Of the sapphire. So it goes like this. The brighter the sapphire, the longer the deposition period. So basically what happens, we have the sapphire here, let's like say this, whoop. This is the luminosity, and here like is the, like see, the sapphire is expanding its layers, its outer layers. So it goes from small to expanding, then it goes back to small, then it expanding again. So then we see the light curve here, so it's gonna peak here, right? And then it's gonna go down again, and then it's gonna go up again. Down, up. So that's the light curve we're gonna observe, right? And that is the luminosity period relation. Luminosity period relation. And that is being used to determine the distance based on the first step. Okay, let's first finish this and then I show you some real data. Okay. So the luminosity and hence its absolute magnitude can be determined by observing the period, the periodical change of the brightness. observing the brightness or variation. And then you use the distance modulus, which this is the apparent magnitude, small m, right? Remember that? Absolute magnitude, big M, and then the distance d, this is -5. So you can just use, you observe basically the period, you know what the absolute magnitude is, and then you can just rearrange it towards a distance here, because we of course know always the apparent magnitude. We can always see the apparent magnitude and rearrange it towards a distance, and thus we get the distance towards the star. So we compare the absolute magnitude towards the apparent magnitude, and that's how we can get it. It's an indirect approach that needs calibration. But before we go into that, I want to show you some real data. Are you explaining redshift? Yes, redshift comes in the third step. I'm just afraid this stream is going on for too long, and it was already 2 hours nearly. So where do we have it? Here. So this is from Gaia. This is observations from Gaia of Cepheids. These are the light curves. So here you can see Gaia's observation of different Cepheids. I think this is one type of Cepheids, right? And what you can see here, let's make this a little bit bigger, is it's given in terms of phase, but the period is noticed on top of here. So this also is in the G band, so the light is taken, there's some light taken in the G band, like it's not all of the light, it's like filtered through a band, right? But here you can see the period, and here you can see the magnitudes, basically, okay? So you know that lower magnitudes mean brighter. So here's a period of 0.3 days, and for a maximum magnitude of like something like higher than 8, like below 18, right? And now the next one has a maximum period of like nearly 18, and the period is larger, just as we said. And now it's even brighter. See, now the maximum is at 70-80, and the period is 0.45. Here we go even to brighter terms, 70.4. And the period is 0.45, and down here we even go all below, like the last one, to a magnitude of 16.8, and it's the longest period, 0.85. So just as I said here, the brighter the Cepheid, the longer the pulsation period, right? And that's what we can see here on the real data of the Gaia data release. Any questions to that? It's very bright. So, and that is compared to the first step, where we use geometry, an indirect approach. And because of that, it needs calibration. Needs calibration. And how do we calibrate this? Use the first step. Find Cepheids that are close enough that we can use the parallax method from the first step to measure their distance. Then we now know the distance. We know their period and their luminosity. We know all of that. And then we can, when we then observe a Cepheid that is too far away to use parallaxes, we just measure their period, compare it to the data from the parallaxes, and we know how far away it is. So we're gonna find Cepheids close enough to use parallax method. Use found distance, yeah. Use found distance. apparent magnitude we can always observe, right? So use found distance and m. Small m is the apparent magnitude, right? To calculate the absolute magnitude. Wait, we just make capital M. The calculate capital M from these ones, right? Here, from the one that are close enough for the parallaxes. And thus, the second step depends on the first step, right? Use this to conclude on distance to Cepheids too far away for step 1. Second step depends on the first step. We use the distance modulus, right? We determine the distance, we know the apparent magnitude, we can get the absolute magnitude, and then get the luminosity period relation. So Cepheids are more massive than our sun, more massive and luminous. Than our sun. Whoa, 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 whoa. Thus can be seen further away. Diameter of the Milky Way, we said 30 kiloparsecs. So basically we can see outside of our own galaxy, yeah? So this is intergalactic scale already. So now we can use the first step to go even farther out, even to the intergalactic scale. So this is suitable for the local universe. Suitable for the local universe. Historically, I wanna tell you this because it's so rare that you can contribute something to a woman in historic science, because, well, they weren't allowed to do shit, right? So this was discovered first by Henrietta Leavitt. Henrietta Leavitt, did I say the number somewhere? Oh, I forgot to mention the year. But anyway, she discovered it. She was allowed to work as a human computer, basically. So she got data, and then they were like, hey, you find out the magnitudes for us and catalog them, right? Yeah, but basically she wasn't allowed to have her own science project. But yeah, she was basically just there to work as a human computer. But while doing that, she even found this relation. So it's really cool, actually. Third step. So for the third step, we use supernova event. And this is another standard candle. As we said earlier, a standard candle is an object where we have a very well-defined intrinsic brightness because of a physical property, right? And in here we have the physical property of how a supernova is triggered and how bright it is because of the triggering. Yeah. So What is good about supernovae? They have an extreme luminosity. Extreme luminosity. They outshine the whole neighborhood, and so can be seen even further than Cepheids. Up to 100 megaparsecs. We went from 1 kiloparsec for the first step to 30 megaparsec for the second step, up to 100 megaparsec for the third step. So that's a big increase in distance, we can see, right? Because of their mechanism, they also have an intrinsic physical luminosity that is based on the mechanism, and can also be used on the cosmological scale because they can see so far away, right? And this is another indirect approach. Needs again calibration. How's it done? Find SN supernova event in galaxy that also hosts Cepheids, which we can observe, right? So a galaxy that is close enough that we can still see the Cepheids and the supernova event. Then we determine the distance with the Cepheids and then calibrate it to the supernova event. And then we can estimate the distance to the galaxies. So let's go back to the ladder. We're keeping that very short now because I'm running out of time. Each step will accumulate uncertainties. We have to find methods that have a low error. We need to reduce the error. Find good methods to reduce error. There are many different indirect approaches, and as I said earlier, it depends on the object. There's, for example, star clusters, planetary nebula, and for example, the whole galaxies. There's something called, I'm just mentioning this here because we're gonna look at that too, the Tully-Fisher radiation, where they connect the brightness of the galaxy to its rotational speed. The last step on the ladder basically is the Hubble law. And just to be clear, I was just looking at 3 steps. There are many more steps. The universe is expanding. Oh shit. Expanding. So the galaxies appear to move away from us, right? Move away from us. Where is it expanding to? That's a good question. Study science and find out. They're not actually moving away from us. It's more like the space in between is increasing. And I want to say this here now. Also, if not otherwise gravitationally bound to us or to each other, gravitationally bound, the space between galaxies is expanding. Unless they're gravitationally bound, then like a galaxy cluster, then the space between galaxy clusters is increasing, right? Not between the individual galaxies that belong to a cluster. Space between galaxies is increasing. just to make that clear. And just to know, any other observer in any other galaxy would see the same. The cosmological redshift is similar to the Doppler effect, but it's not actually the Doppler effect. The Doppler effect gives us basically the velocity that the object had at the moment it was sending out the light. And the cosmological redshift is actually stretching the photon because the space is stretching. There are other reasons the photon can be redshifted. Okay, so let's say, for example, galaxies have also a peculiar velocity, right? Velocity have also a... Okay, I wanted to make it short and now I'm just adding something. Great. Peculiar velocity. Why do they have a peculiar velocity? It's because they're gravitational bound to other to other objects, right? So they also move away from us maybe for other reasons, or they even move towards us for a short time for other reasons. Yeah. Okay, let's say have also a peculiar velocity due to gravitational effects. And I just wrote the fact. So we have a local group, right? We also have a local group. Andromeda belongs to our local group, and also a lot of dwarf galaxies belong to our local group. And this local group is gravitational bound, right? And our galaxies have a peculiar velocity due to the gravitational effects. But the space between them is not increasing due to expanding of the universe, because we are too gravitational bound to each other, right? That gives us a peculiar velocity. But the farther away a galaxy is, the more insignificant does this effect is this effect. Velocity of galaxies further away will be dominated by the expansion effect. Remember at the beginning, right? When we said, well, the mass of the sun is way, way bigger than the mass of Earth or any other planet in our solar system. So let's just throw it out, right? And this is the same. Eventually the redshift, because of the expansion, will become so massive that it's gonna, it's completely dominating. It's a completely dominating effect. Any kind of peculiar motion they had is completely overshadowed. So now we're gonna write down the Hubble law. Hubble law. So what is the V? It's the radial velocity. Radial velocity. The radial velocity is the velocity the galaxy has away from us, right? That's why it's radial. Then we have here, of course, the distance, and we're talking about a proper distance. In cosmology, there are different kinds of distances, and this will become important eventually, because this is a very simple formula if you look at it. But it's not as simple anymore when we go to higher distances because of that d. But for now, let's say it's a distance, and that's it. That's all we know. That's all we need now, yeah. And this is the Hubble constant, right? Hubble constant. This is a 0 here, h0. So the farther away a object is, the faster it is moving away from us. We can rearrange this to the distance, right? We rearrange this to the distance, so we then have d equals v divided by the Hubble constant. So we need to find v. So we can find out v with another formula, which is speed of light c and the redshift. And now we're gonna go into the redshift. Now we're gonna go where the redshift comes from, right? So then the formula becomes this. The radial velocity of a galaxy can be measured with its redshifted spectral lines. And I wanna... Okay, let's do it like this. So here's a star. Okay? Let's say we have an observer in this direction. We see all the light. Let's say there's interstellar gas here, like a gas cloud. Okay? We don't see all the light anymore. We only see like, we're gonna see the spectrum that we see here, like the spectral energy distribution. And we're gonna see absorption light, because some of the light is gonna get absorbed, yeah? So some photons will be absorbed. And now, what we also see though, if we don't look at the star anymore, but at the gas cloud also shines. Cloud itself radiates light. How is that? Well, when the photons get absorbed, and then basically all the electrons or whatever in the cloud, like they bounce against each other and they de-excite and excite atoms, and then eventually an atom is gonna de-excite again, so the electron is moving to a lower state. The photon is gonna get released again by a certain element, by a certain excited state, and then it shines as a form of emission line. So if there is an element in this cloud, because of all the radiation from the star, it ionizes the gas and then it's getting de-excited again, and so the cloud is giving away light as well. And now I want to show you the picture that we got from the... I think this is fitting. I think this is fitting to here. So this is from the you may have seen it. You might have seen it, right? If you looked at the James W pictures, James Webb telescope, I mean. Here it is. These are the emission lines I'm talking about. So this is from the deep field view, right? And here they say that they don't really give the redshift, okay, but it goes to lower redshift, right? And you can see here the wavelengths of the light. You can see this, the oxygen line and the hydrogen line here. These are the same lights, but you can see they are at different wavelengths. Why are they at different wavelengths, even if they're the same lines? Because when they're further away, the more redshifted the light goes, right? So this galaxy here is further away than this galaxy, so it's shifted more towards the red. This is very, very far away. That is when we talk about cosmological redshift. We also use this interchangeably, right? This is used like in astrophysics, instead of saying how far away something is, we're gonna just give the redshift. That shift in spectral lines we compare to the value in the laboratory. So just to write this, okay, so Z is the redshift, is given by, so this is the wavelength, So this is the wave, like, okay, emission line. So we have the number, the wavelengths that is observed. We subtract the wavelengths that is emitted, divided by the wavelengths that is emitted, and that gives us the Z value. All right. So this hydrogen line here has a laboratory value, which is the emitted value, right? There's a number here it has, I don't know what is 2.6 or whatever in microns. And that is the observed value. But when it was emitted, it had a different value, right? Because it got stretched due to expansion on the way towards Earth. I just also want to point out that this formula here, or like, that basically goes for Z that are smaller than 1. Or even less than 1, like maybe even Z smaller than 1.8. Everything larger than 1, it's not gonna be that easy anymore. Okay, I want to stop now because I had a little bit more to all of that. I can't think anymore. We started out with the cosmic distance ladder. We talked about why is it important. We looked at the solar system and how they historically derived the distance to planets with the Kepler's third law. How they derived 1 AU with the Venus transit. Or actually just a little bit. We looked at what magnitudes are, apparent magnitude, absolute magnitude. And then the first step, which was the trigonometric parallax effect. The second step, which was the Cepheids, right? And the third step was the supernova. We kept that short, and now we went through all the last step of the distance ladder, the Hubble law. Alright guys, I hope you have a nice rest of the day, of the Sunday. For some people Sunday is already over, of course. Looking at you, Australia. And I hope I will try my very best to make the next science stream by the end of next month. I really try, and until then, and yeah. Thanks so much, guys. Live long and prosper.